I don't know if you guys know him or not. Fourth years definitely know him because he teaches there. He stays second floor AC. And studying accretion dynamics around the neutron star and trying to change a code which is written for black holes and convert it for neutron star to simulate a magnetosphere around the neutron star. I'll tell you what is magnetosphere later in the talk, but that's about my work. So today I'll talk about accretion. This is a animation I took from NASA Goddard Space Flight Center website. This is GRS 191. It's a main sequence. So this white thing is the main sequence star. So it's a star, bigger star. And sorry for the language. I'm very chill here currently. And that's a black hole, small black hole. It's a material system. Sorry. And so what you guys see around that glowing thing, red glowing thing, that's what you call accretion disk. So what is accretion disk? So you must have seen these images in the 2017-2019. It must have come used a lot because this was the first image of a black hole. So black hole is called black hole because it's fully light can't escape. So how do you image it? So the only way to image it is to image the accretion disk around it. So this glowing thing is the accretion disk. Now, why does it glow so much? Like you can say that at any object with non-zero Kelvin temperature will emit a black body radiation. But it's not enough to explain this luminosity. This luminosity is like 10 times higher than our sun's luminosity. Okay, it's very high luminous. So what is the reason behind it? So why do you study these accretion systems? So it's because it's for curiosity purpose, because it spins and it glows, that's it. Because you must have played in your childhood with some spinning top or something like that. So it's like a child's curiosity, like yeah, it spins, it glows, so that's why I studied it. But you can't say this to the funding agency that I want to study this, so please give me money for that. You tell them something else. What you tell them that so these systems are very extreme environment, these are extreme physics happens here. So this is like a live laboratory there. So the only way to study them is to image them, and you get live experiments data coming from there every time, every second. So that's why you send satellites in the space. So if you know about India's first satellite, which studies accretion, like the quasars and pulsars, ExpoSat recently, around 2 years back, it was released from. It was under IISER only. So I talked about where does the glow comes from. So accretion is essentially what? Like high gravitational object is attracting material due to gravity. Okay, it's purely gravitational energy which just gets converted to a luminosity. So imagine you must have done this problem in the 11th, 12th also. You take a mass at infinity and you bring it to a point at some finite radius. So what is the work done? It's minus gmm by r. So that is what I've written here. But I have multiplied by c square on up the numerator denominator, and what I get is that this mc square, you guys know, rest mass energy. This simple rest mass energy. So gm by c square r, if you calculate it for a solar mass, like for our sun's mass, but take a radius of like 10 kilometers. Okay, that's the usual radius of neutron stars. Okay, neutron stars are very compact objects with a very high density per meter cube, but the high density means of what? Like very small radius, but very huge mass. So mass can be up to like solar masses, 10 solar masses, 100 solar masses. There are people who observed like billion solar masses also. Some stars have been, compact objects have been observed till now. So that is what this glow is, like the gravitation. So when you calculate this factor gm by c square r, it comes up with 0.15, which is very high fraction of a rest mass energy. You must have seen that when you throw water from a height, it converts to electricity. But our tap water can't do that. Okay, it's a very small amount of energy because it's a very small amount of water only. You need large amount of water to get converted into electricity first. So that's what this is actually, if you think about it. This is exactly what happens in accretion. There's a large amount of mass which get accretes from large distances towards the neutron star and get converted into energy. That energy is what radiated as luminosity. This is what accretion is overall. So there are many ways that accretion can start. This is one of the very well studied way. This is called Rho-Slope overflow. So what exactly is Rho-Slope overflow? You must have studied, you must have learned Aditya L1, right? So you guys must have questioned what is L1 there. Right? I don't know if anybody of you guys, if you know what is L1. So what exactly is L1 is that at a point, between two objects where gravitational attraction between two objects and centrifugal force in the rotating frame is 0. Okay, so any object placed on this L1 point will not face any forces. Okay, it's equipotential surface. You must study in 11th also. Calculate the equipotential distance. Okay, so that is what is L1 basically. So you have you consider two objects, a star and a compact object like a black hole, neutron star, a white dwarf. Okay, now you know our star also is expanding slowly. As the fusion goes away, so currently it's fusing hydrogen helium. Okay, then it will go to higher mass elements. It will eventually reach iron because iron is the most stable element. So when that happens, the radiation pressure which comes out of that fusion reaction, that radiation pressure will exceed the gravitational force which is contacting it inside, and it will basically expand in size. Now, suppose if that happens for a companion star like this red star, it will overflow into the gravitational influence region of the small compact star. That means first it was very small, it was well inside the gravitational, it was the compact object was not affecting its environment. Compact objects, neutron star suppose, is not affecting its giant star's surface, but it got expanded and it enters its region. Okay, now once it enters its region, it starts capturing the material from the star. Now that's what I am showing here. When so you can see that the red material, it gets overflow and then it enters the gravitational influence region of that blue thing, which is some white dwarf. Okay, this is how, in a simple way, accretion can start. One of the way accretion can start. Now you know a star is also rotating. Okay, now you know from Newton's first law, any object is, if it's in motion, it will stay in motion. It doesn't external influence. So if the star has a rotation, any matter coming out of it will also have some angular momentum. So this matter has a very high angular momentum. So it will kind of like spiral down towards the compact object, white dwarf, neutron star, anything. So there is a lot of angular momentum coming in from the external object. You keep this in mind. I'll come to this point later. There are other ways of accretion can happen. This one is a tidal disruption event. So you know an object the orbit is elliptical. Like that's Kepler's law. Okay, so that means there is a point of closest approach, there is a point of farthest approach. Now if there are two objects whose closest approach is inside the gravitational influence of the compact object, that means whenever it reaches the closest approach, this compact object will capture some material out of it. It will kind of force the material out of the companion star. And when it again goes farthest approach, it is out of the gravitational influence of the compact object. So at each maneuver, after each maneuver, it will keep ripping out of some materials out of the companion star. And eventually, you can see that T equal to 0, that unbound ejecta. So it's like it's going like this. It enters the gravitational influence of the small object, and it's like it takes out some matter. T equal to some hours, T equal to some day. Now you can see it has become a very thick circular region. Like the companion star is gone. It's done. It is dead. Like it's fully lost its material to the compact object. After that, in a few days, it will form accretion disk around it, and it will keep getting material from that star's material. This is one way accretion can happen. Another way, this is a very ideal case, but it is very well used as a test case to study these real physical cases. This is called spherical accretion, which is what I will be focusing in my talk. Spherical accretion is basically matter coming from all sides. In accretion, there is a plane in which matter comes. Okay, like even our solar system, it's an example of protoplanetary disk, which is in the plane. Uranus is the exception, which like kind of orbits outside the plane. If you guys have studied about that also, so that is a different reason altogether. But essentially, why we have a disk? Because of angular momentum, which I was talking about before. So in this case, matter is coming from every side, like 2% inches हर जगह, ठीक है? So this is spherical accretion. This image I took from my own work. So I talk about accretion disk. How does accretion disk form? It has something to do with angular momentum. Okay. Now you consider there is an object. There are two rings. Okay, you must have studied about that inertia, moment of inertia. You have a small arm, it will rotate faster. Large arm, it will rotate slower. It's the same thing. You have differential rotation. Like, there are two rings, one inner ring and outer ring. Inner ring will rotate with a higher angular momentum. Outer ring will rotate with a lower angular momentum. Okay. Now, if these two rings come in contact, one of them will try to pull each other because of viscosity, right? The higher angular momentum, which is rotating with a higher angular velocity, will try to speed up the outer ring, but the outer ring will try to slow down the inner ring. Okay, that's because of viscous forces. So you can you can use simple centrifugal force equating with gravitational force, because that's how the rings are forming. Because you have a balance of these two forces, and that's how you have a circular orbit, right? Circular orbit is basically gravitational forces and centrifugal forces balance. So this is what you get as a formula for angular velocity, which varies as 1 by r cube. So differential rotation. Okay. Then because of viscous stress between the two rings, you have angular momentum getting transport between the inner ring and outer ring. What do you mean angular momentum transport? I said just now that the inner ring is trying to speed up the outer ring. That means it is trying to transfer some angular momentum to the outer ring. When you transfer angular outer ring, it will speed up. Okay, so that's what happens in accretion disk. Suppose you have a big, thick disk, thick column of material, and you rotate it in a very fast way. It will spread out, right? That same thing happens in accretion disk. You have a very thick disk of a thick column of material, and because there is angular momentum associated with it, because the companion star was already in the rotation, it becomes accretion disk, a flat rotating material. Okay, that's accretion disk. That is the real physical scenario which we study using simulations and everything. But what happens is your code which you write needs to test it first, calibrate it first. Calibrated means you need to put some ideal cases, any cases which you know results from data observation or theoretical, like you have solved it theoretically using non-mathematical formalism, and you want to test it in the code, and you want to match the two results. If they are matching, that means your code is right. Whatever code you have written is right. So what you do, you spruce up this ideal case like spherical accretion, where matter is coming from all the sides. So when I said there is a matter is coming with a high angular momentum, it can happen that a matter does not have high angular momentum at some radius, but the gravitational force is dominating the angular momentum. So like what do you mean high angular momentum in there is a high theta velocity, right? Like in the r theta plane, you can say when there is high theta velocity, that is the high angular momentum case. And when the matter is coming directly radially inward, so that means there is a high radial velocity. This is just a term which we use in literature or called subcaplarian flow, which says that the radial velocity is higher than the theta velocity. Okay, and another example is Keplerian flow, which I was just explaining before, where your angular momentum is high, so it will keep rotating in the same circle unless there is a viscosity acts on it and it goes to inner circle. Without viscosity, accretion cannot happen, which you probably may have realized by now. If viscosity was not there, ring would stay stable at that same point. Accretion cannot happen without viscosity. So this is Keplerian flow. Now I have written the title of the slide two-component adaptive flow because in 1995 there was this Chakravarti who is also the PI of my PI. He gave this model which is currently one of the best model which explains the observed results, observed data of accretion disk around neutron stars and black holes. So this is the reason why I am studying this model also. Okay, so let's come to spherical bonding accretion. So this guy Urban bonding, I don't know if you guys know about it. If you guys have studied about cosmological models or something like that, this guy is the one who gave the first ever steady state cosmological model, which says universe has constant density. But now we know it's not like that. It's constantly evolving, it's constantly expanding and all that. But this guy, 1950, 1940 or something, he gave the first steady state cosmological model. And basically, what was going on in his mind that at that time, people were trying to explain sun's luminosity. Now, this whole lab, this Cessi lab, is trying to basically solve try to understand how sun's luminosity varies and why it varies so much, and how to predict it in the future, right? What the high luminosity will be and what low luminosity will be. We want to understand how the sun's variation happens in time. At that time, in 1950, they were trying to explain that phenomena of sun's luminosity variation using a model called so they thought that because our sun, along with its all planet, is also moving in the spiral of a Milky Way galaxy, right? So that means, suppose it is moving in a vacuum, suddenly it encounters a nebula, a gas, okay, and that gas is what, and when the gas comes in encounter with the sun, it accretes some matter from the gas, and they thought that this periodic accretion or non-periodic accretion, like this, whenever sun will accrete some gas from the nebula, the luminosity will go up. And they thought this is the reason why sun's luminosity varies over the 11-year cycle or 12-year cycle or whatever. But now we know it's not the case. It's purely because of internal dynamo and everything that's why these guys are studying. Okay. So, but what he stumbled upon was a very ideal problem of a steady mass, a steady rest mass in the environment of a very large gas, and trying to find out how fast it is accreting, like how much grams of or how much kilograms of mass is accreting per second. That's what he wanted to understand. That's how this guy gave rise to the accretion disk field as a whole. 1952 was the first time this guy wrote a paper and basically said that the calculations he did in that paper, which gave rise to this big field, he said that this was not much more than an examination exercise for him. This was the first ever paper on spherical symmetric accretion. This is where accretion started as a field. And the paper he wrote, he said, it was the most easiest calculation he has ever done. But right now, nobody teaches the calculation in the undergraduate course because it is frankly very involved calculations and very mathematical. So I just wanted to show that. Because if you guys, if anybody wants to see the calculation, they can go and see that. I have given the paper anyway here, so you can look it up. I frankly am very impressed by the way that time they used to do calculations. Nowadays it's mostly simulations because you can't really solve that complicated mathematical equations on paper. Okay, but they found a very niche way, very creative way to go around it and found some approximations and did some very nice creative maneuvers. Okay, and they wrote this paper. He wrote this paper after the many papers came. So, before going into this spherical symmetric accretion, anything like more than 90% of the matter, 90% of the objects, not matter. I would not say that because we all know that the dark matter is the most dominant matter in the. But whatever. So we use fluid dynamics as a tool to understand, to model these objects. Like sun also we use MHD. Accretion disk also we use fluid dynamics. if fluid dynamics if the accretion disk has a magnetic field in it, we use MHD in it. So before going to the little bit maths, I would just like to introduce what is hydrodynamics, what is fluid dynamics. So fluid dynamics is just an approximation. Okay, it's nothing much more than an approximation. You zoom into a quantum level, you have to solve Schrodinger equation. You can't use fluid dynamics there. These atoms are interacting. You can't ignore their interaction when you are that small at that level, at that length scale. You zoom out a bit, you zoom out enough that you can imagine them, that you say that there are enough amount of collisions happening in the gas that at any volume you take, at any some length scale of volume you take, thermodynamic equilibrium is maintained all the time. Thermodynamic equilibrium means the temperature is constant. Okay, between any two volume, temperature is constant. That's what I'm saying. That hydrodynamics says that you go to a length scale where you can establish a thermodynamic equilibrium. Now, what is the length scale? When I say how is the thermodynamic equilibrium maintained? With enough number of collisions. Collisions should be there. There should be a lot of collisions. So, how do you characterize the collisions? Mean free path. You guys know mean free path? Mean free path is basically average distance between each collision. So if you have large number of collisions, mean free path is very small. So you can take any, all you have to do is you have to take a length scale which is very larger than the mean free path of the particle in question. Okay, you consider air, like for us, air is a fluid. Because air particles, mean free path is very small for if you compare our length scale. Okay, and collision time is basically the time it takes to collide. Okay, so your time scale also should be very larger than collision time. If it's less than collision time, that means collision is not happening only. Okay, so if you go less than collision time, collision नहीं हो रहा. So what you want to do is you want to take a length and a time scale very larger than the mean free path and the collision time respectively. That is a fluid approximation. There are more when you come to plasma also. The plasma has magnetic fields. You need to consider something more approximations also. But for fluid dynamics, this is more than enough. The key equations, okay. So the first equation is just mass conservation. If you see del rho del T, mass changing with time. I don't know if you guys know grad operator. You guys know grad, right? Good. So grad of rho is basically saying how mass flux changing through space. So I think intuitively you should imagine that if through an area a mass flux is changing in that volume, the rho will change in some time. So that's what continuity equation, and what it says is whatever mass is going through it is changing in space. That's it. That's mass continuity equation. Second equation is, if you see the first term del V del T is essentially force per unit mass. If you think about it, acceleration written. Okay, that's just force per unit mass. If you see the whole equation is essentially force balance equation. It's essentially Newton's second law. Okay, we are balancing all the forces in the system. Second term is advection term. Advection is basically any fluid particle, any fluid volume carrying some velocity with it. Okay, carrying some momentum with it. Okay, that's advection term. Third term, if there is a pressure difference between two objects, it exerts a force on it. That is a force due to pressure. F is any external forces which you want to add in the system. Gravitational force, magnetic, Lorentz force, electric field force, any force you want to add into the system. That's what goes into this. And the last is grad square V. It's basically viscous force. Okay. Now, if you guys know about this equation, second equation, this is the most famous equation in the world, Navier-Stokes equation. Its solution is still people don't know. There are mathematicians who are still trying to figure this out. They're trying to prove that whether solution exists, or they're trying to prove that the solution don't exist. I think Shishindu sir works on this only. So Shishindu sir, I don't know if you guys know it. First year don't know it definitely because he just vanished after us. So I think second year probably no. I don't think there any hack either. But so he works on Navier-Stokes. So you can ask me that how do we use this if you don't solution of it? what we do is we do numerically solving, we do numerical simulation. We don't do analytical solution. We can't solve the analytical because it's a very, so in first year we were, I think me and Mac only taught you about linear ordinary differential equation, homogeneous ordinary differential equation. But we also told you that the non-linear ordinary differential equation is a very hard to solve. There are only few solutions there. This guy here is a non-linear, non-homogeneous partial differential equation. This is just out of this world. Okay, you can't really solve it analytically. It's very complicated. What you do, you make some approximations, or you solve it numerically on the computer. That's what I do. And also, don't forget equation of state. There's no equation of state, right? A relation between pressure and density. So, like, I just see this P equal to P equal to nRT, adiabatics P equal to K raised to gamma. So, let's come to spherical symmetry accretion. So, few assumptions before that. It's just the assumption which went into solving spherical symmetry accretion was steady state accretion. That means no time variation in the accretion. Okay, the accretion rate, whatever it is accreting per second, will not change with time. Okay, if it's accreting 5 grams per second, it will stay throughout the time. Okay, and adiabatic condition. I just said P equal to K raised to gamma. That's the equilibrium state I am assuming to solve my problem. You start an equation of continuity. Okay, equation of continuity I showed you before. Yeah.
Is there a reason you are assuming adiabatic conditions?
Yeah, because I told you, right, these guys 952 they didn't have much computation power. So what they did, they assumed some very basic problem, very ideal problem, and they tried to extract some kind of they can interpret the results and match it to physically observed result. And like it's actually admiring that this form m dot equal to 4 pi r square rho v. It's even though it's based on a very idealized assumption, it is a very close approximation to the current observed data. This result gives a very nice approximation to the what we observed. We observe accretion rate, and we want to calculate luminosity from that. So this works well in that case. Okay. So what is exactly I'm doing? Ignoring the time dependency, and because it's spherically symmetric, so it is coming from all this plane. Theta phi plane, all r direction सब जगह से आ रहा है matter, सब जगह से आ रहा है. So what I do is I integrate over all the volume. What I get is basically m dot equal to 4 pi r square rho, which basically says if I go to a smaller your accretion rate will depend on the density of the matter which is coming in, velocity, and at what radius. But I said just now the accretion rate will stay constant. That means if I go to a smaller radius, the V has to increase. It has to cancel out everything. To keep the accretion rate is constant. And I think I told you just before that as you go lower and inside, the angular velocity and the radial velocity also increases. So that's what m dot is. Moment of observation. Moment of observation is
Yeah. The question I want to ask, to viscous force acts the same way like it did on Earth and it did in accretion disk. Do viscous force acts the same way?
Viscous force, what is the work of viscous force? It's just it's dragging, it's a drag force, right?
Yeah, so we have a different equation for water and other fluids in Earth.
Okay, so listen, actually, I think what you're trying to say is the molecular viscosity, right?
Yeah.
So that's a good question actually. So molecular viscosity, people thought that molecular viscosity is the source of this viscosity in accretion disk also.
Yeah.
But the predicted accretion rate, which they calculated from assuming molecular viscosity, was very small. So essentially in accretion disk, the source of viscosity is not molecular viscosity. So whatever you guys have learned about that 6 pi r eta, whatever, I know that's what you're asking me. Yeah. That's what you're asking for so long. Okay. So that's not the source of the viscosity in accretion disk. The source of viscosity is not known. Still, it's an open problem. What they did to bypass this, they gave a alpha term. They told that this alpha term is what will denote viscosity. They told that this alpha will have some value less than 0.1, and whatever source of viscosity, we don't care, but the magnitude of the viscosity is characterized by this alpha term. there are researchers who are trying to find out the source of this viscosity, which is another research field currently altogether. And there are people who basically say that we will solve the fluid dynamics equation, the emission equation, from base, from ground zero in computer coding. You write some code and you say that the viscosity will naturally develop. We don't know how, why, it will just naturally develop. Okay, when you solve the equations of fluid dynamics, it will just develop on its own viscosity. Viscosity is already.
The fluid is in turbulent regime, that is one of the sources of viscosity. So,
Yeah, but in
the
the turbulent regime is only possible in the magnetic.
not magnetic turbulence. In hyperplus also you can have turbulence. There are also some effects that critically.
Okay.
And that acts as a source of viscosity.
Like as far as I know that there are many MRI also people given out as a source of viscosity, but there is no observed result, observed experience. What experience? Observed data to say that this is exactly the source of the viscosity, and then so be able to.
So without the source, how did they characterize alpha as like 0.1?
So you say that a matter has to accrete only if it has more inward. When a matter moves through space, it has some momentum. So that momentum force should be more than the any radiation or anything. Any force which is trying to not let it come inside. And how to explain this? Okay, so let's say in the case of neutron star, it has a magnetic field. So the magnetic field acts as a wall to any matter coming in after some radius. Imagine there is some radius after this magnetic field does not allow any matter to come in. So what happens is that this momentum force needs to exert large amount of pressure on that magnetic wall to accrete, to start accreting on this object. So people made this model. People knew that this has to happen. Whatever matter is coming in has to penetrate the magnetic field of this object. So they made a force balance condition: magnetic force and the pressure force. When these two you equate, add alpha term to the pressure term, and you say that alpha is equal to ratio of these two values, magnetic and the incoming matter. And you say that this alpha must be so what I want to happen is accretion to happen. So what I want is this momentum force, which I was telling, which should be more than that. So that means this alpha should be some large value or something. Or you can take the ratio ulta and then you say alpha is very small. Okay, that's how they try to mathematically write it down. But they don't know why. What is alpha? Why is alpha? It's just there, and you calculate numerically, simulate it, and find the approximate the most accurate value for alpha for this accretion can happen. Animation also. It's like a small model which I made. I have a good drawing experience. So when you so these equations I did not solve in any complicated codes. I just did in Python. I don't know there is third year here, but third year when they teach computational physics, they teach you how to solve coordinate differential equation. So you can just solve this from there. If anybody wants to know how to solve it, they can come to me. I can show you my code. But solution you get is something like this. So like I told you, as you go closer to closer, the amount of volume which is there is very small. As you go very far away from the star, amount of volume is very small because the radius is very small. So if you create a radius of some r greater than the radius of the star, volume is smaller than the outer area. So the density must increase there to keep the accretion rate constant. Okay. Similarly for velocity must increase. Okay. So the velocity as it starts from outside, this is basically a radially informed. There is no angular momentum in this. There is nothing. This is radially informed material. So when you solve these equations, what you get is a transonic solution. What is transonic solution? So transonic solution is basically a matter which starts subsonic That means its velocity was less than the local sound velocity, right? And as it comes inside near the star, it crosses a point of transonic point where it becomes supersonic from subsonic. Supersonic is when velocity is more than local sound velocity. You must have seen that aircraft going at high high speed, Mach 1, Mach 2. That Mach 1, Mach 2 is basically Mach number equal to 1, Mach number equal to 2, Mach number equal to 3. That means the velocity of that object is more than 3 times the sound velocity. So it crosses the pressure barrier, like it breaks the pressure barrier formed by the air, and that's why we get a cone kind of object. And you see you picture a supersonic jet. So this is the kind of solution you get when you solve this equation. Now
What do you mean by local sound velocity?
so air has a sound velocity.
Yeah, but in space, how there is a sound velocity?
Okay, so you know sound. You know what sound velocity depends on? Density and pressure.
Yeah, density and pressure.
Exactly.
Yeah.
So if density of pressure somewhere changes, sound velocity should change.
Alright, so you're talking about accretion, particles and all.
Anywhere density pressure, if you change it, in water density is different, sound velocity will be different there.
Yeah.
So
Fine.
yeah, you got it. Right? So now the computational part, that was just initial conditioning. Now what I want to see whether my code is running correctly or not. So I will put that test condition into my code and see whether it is giving me a steady state accretion. That means my accretion profile does not change with time. So you have some initial condition which we just saw before. You put that in a code. This is the structure of that code. You don't have to go into this, but this is a Fortran code which I work with, and you can actually also play with it, and you find like you can learn about what goes into that code, what kind of algorithm goes into, what kind of study they do, what kind of PDs they solve, and all you can study. There are very nice lecture notes by Professor Kasar. You can scan this QR code and you can learn about it. Okay, there are very in detail lectures about how to write algorithms for PDs. Okay, but what essentially you get from this code is basically your tiny remote solutions of your initial condition. Once you have the time remote solution, you want to visualize it and see whether it is actually. Okay. So this is what you get. At initial condition, this is what the profile is. On the color map, it's density scale. So very bright color, basically high density region, and very bluish side is very low density region. That's what we saw in the when I saw the 1D profile. Density increased as it reached the inner radius. That's what it's showing here. In a contour plot, the density is increasing, and as you time evolve it, you put the potential into the code, you again get the same result of it. That means the code is running correctly. The code is able to imagine the physics properly. Now, like I told you, neutron stars, white dwarfs, and even black holes, they can sustain a magnetic field. Okay, now so you cannot really do normal fluid dynamics. Fluid dynamics does not involve magnetic field. So you include magnetic field in it. So when I say magnetic field inclusion, that means you want to include the Lorentz force in it. Okay. Now, when I showed you the Navier-Stokes equation, there was an F term. You put the Lorentz force there. When you do that, you get this equation. Okay. It's very complicated, but I can. So there are only two extra terms you can see here: the v square by 8 pi and the v dot grad times v by 4. That's the two extra terms you can see here. Okay. Now v square by 8 pi, because it is with pressure, that means you know that it's also a pressure kind of term. Pressure due to magnetic field. You can, so when you go to astrophysics realm, when you go to that length scale like of parsec, even at suns, like sun also you assume, there the magnetic field starts to behave like a string. Okay. This may be a bit magic like that, but it behaves like a string. Like in 11th, 12th, you must have studied the magnetic field and can't cross each other, can't touch each other, because magnetic field vectors will be same at say at the one point, right? But there are many things bizarre happens, and it happens. Okay, and this is basically a magnetic pressure term, which says that if there is a lot of magnetic field at some volume, it will exert some pressure. Okay, any material which is coming. And the next term is the tension term. So I just told you, imagine the magnetic field as a string. String has a tension, right? So there is a length after which it can't expand. Okay. So that's a tension force which is trying to hold it in place. And magnetic pressure, which is like you were trying to bend the string. So if you bend it enough, and tension is also there, it can break, right? So you assume that there are two people holding the magnetic that string from both ends, and full tension force is there. It is fully straight, and now you are trying to hit it with like in the middle. What will happen is that at some point that string will break. Same thing happens in magnetic field also, with magnetic field. If the matter is coming with a high momentum, and the magnetic field is weak enough, you can break the magnetic field lines there. I mean, it's not as if magnetic field lines, there's a lot of terms involved there which I don't want to go into complicated thing. But just for you now, basic picture, just want to give you that magnetic field lines, like they just break, and this is open, and matter comes in. That's what I was trying to tell you before, that magnetic has a wall. It acts like a wall, and it doesn't allow any matter to come in. So this curve 8 pi acts like that wall. This is a magnetic pressure which is holding, it is not allowing anything to come in. So that is the magnetic force tension and the magnetic pressure. Now in your system, there is one more quantity called magnetic field. So you want to know how the magnetic field evolves. So you need a magnetic evolution equation, which is called magnetic induction equation. Okay, this is like I said, Navier-Stokes is the most beautiful equation. This is magnetic equation. Okay, there is so much stuff you can do with this. Okay, like you can derive this using Maxwell's equation. Okay, Maxwell's equation, I think you know. So you can derive this equation Maxwell's equation. You can also cite some. If you cannot do it, you can cite some books, and you'll find out. But essentially, you had the continuity equation. The Navier-Stokes became like this. This is now MHD. Now you are in the realm of MHD. You have continuity equation. You had Navier-Stokes equation. You have magnetic induction equation and equation of state. And I forgot to mention one more equation, which I don't know why you guys also did not think of, an energy conservation equation. Energy conservation equation I did not write anywhere, because in the last the steady state accretion, it was adiabatic condition. In adiabatic condition, energy remains constant because there is no entropy exchange. Okay, so in adiabatic there is no heat exchange. So there is no you don't need to worry about energy conservation. So that's why I didn't write about energy conservation law there. But there is an expression for energy conservation in fluid dynamics also. And similarly, in MHD also there is energy conservation equation. Now you have put the magnetic field in the Navier-Stokes. Now the magnetic field is coming from the star. Okay, the star has a magnetic field. So when a star has a magnetic field, you assume usually dipolar nature, like our Earth, or I can't say sun doesn't have that. I would have said sun. But okay, Earth and other some planets, they have dipolar nature. Okay, neutron star also there are various theories. There are people who think that it is not entirely dipolar. There are higher order moments, like higher moments in the sense quadrupolar. I don't know if you guys know quadrupolar. Never mind. Just assume dipolar for now. Okay, dipolar means there is north and there is south pole. So this is just an equation. Okay, you don't need to worry about it. But you know the dipolar field falls as R cube. Okay, and that A phi is the vector potential, because you can write B magnetic field as a grad cross vector potential. Okay, that's what I've written. But this is how it looks in the code. Right? You can see there is a this dipolar nature. Like the magnetic field is coming out of the north and it's like going like this. This is dipolar nature. Okay, and so I was explaining to her also that magnetic pressure acts as a wall. Now, so what happens is at larger radius, matter has at larger radius, magnetic field is very weak because it is falling as 1 by r cube. Right? So here magnetic pressure is b square. That means it is falling as 1 by r6, 1 by r raised to 6. It is falling very fast. At larger radius, magnetic field is very weak. But you have matter coming in. So matter can freely fall. Magnetic field will not act as a wall there. Magnetic field is like funnel. Okay. But there will be a radius, at some radius, where the magnetic field will stop it because there is a tension force also there. At larger radius, you can consider only magnetic pressure, which is fine because the magnetic tension is b square again. So at larger radius, b square will be very small value. You can ignore magnetic tension force there. Okay, and b square also very small value. But at smaller radius, magnetic tension will also dominate. So now you have a string which is not allowing any matter to come in. So Lorentz force, you have matter coming in. If it's not allowed to go inside the magnetic field is now very high tension, and the magnetic pressure also very high. Then it's not allowing any matter to come in. The only where it can go is along the field length, because along the field length there is no Lorentz force. Right? Force is V cross B. So if I move along the B, there is no force. Okay, the only where the matter can go is along the field length. So what happens is you have this matter going, following the field length, and where the field lengths touch poles. So they will all come to poles. So this is what is called magnetosphere. Magnetosphere is what? That at a radius where magnetic pressure, which is of the magnetic pressure of the star, and the incoming matter is equal. So magnetosphere, Earth is a magnetosphere.
This is why we see auroras on poles.
Yes, exactly. This is why you see auroras on the North Pole. But there have been cases in the past where people have seen auroras at lower latitudes also. Right? Not just at North Pole, but at lower latitudes also. And that can happen if the matter has very high ram pressure. Okay, very high magnetic field also. Okay, and that's where other things you have to start worrying about. That's what we also, the whole lab also. And below is just a simple equation which I calculated for, like, when you equate b square by 8 pi, which I just told you, magnetic pressure, equals to the momentum pressure. You can calculate the magnetospheric radius where it will form. So I just said the matter cannot penetrate, right? It has to follow the field line. So inside the magnetospheric radius, you can assume it's vacuum. Matter is not coming inside. Everything is outside the magnetospheric radius, and then it follows it. That is a very ideal matter. So there is something there. It's very small. For the sake of simulation, we just give a floor value, a very small value there. So this is what we got from our simulation. When we simulated it in our code, we were able to see some kind of bending. Bending, when I say that it is not able to penetrate inside, it is starting to follow the field lines and coming on the probe. You can see in the first image is the dipolar nature. In the second image, this is not these vectors which you see are not magnetic field vectors. These are velocity vectors. So, like, matter is coming from every side. It encounters a radius where it cannot penetrate, and it starts to follow the field. It comes to the pole. So, and that's it, I think. Yeah. So that's what I wanted to explain to you guys. There's hydrodynamics, there's chemistry, there's magnetosphere. This is what I am trying to model in my thesis for an electron star, which has a very complicated stuff to do because these magnetic fields are very strong, and your average codes, like as far as my code is concerned, the code which I am working with, it's complicated to maintain that magnetic field in the code. Okay, because you have to worry about divergence. Divergence of magnetic field is 0, right? Physically it is fine. Physically when analytically solve it, it's all fine. But when you do it in computer does not know that law. So you have to enforce that law in the code that every time step you check and you check that divergence is always zero. There are these complications which occur which you want to change, calibrate, do again and again and again, and you want to make a code which can simulate a magnetosphere of a neutron star to a good fidelity. Okay, so that's it for my simulation, for my talk.
How do you define fidelity of the magnetic?
Huh?
You said with the good fidelity.
The trust for the code.
Good at saying that how do you know that your code, whatever you are doing is correct? Like how?
So you have some observed data, observed result, observed luminosity, observed all that. So you match it with that and you try to. Like my spherical efficiency is what I was trying to do to test if it has high fidelity. Thank you.
The domain that you showed is that this plane or original plane of the star, which plane was that?
And you can see it's like a matters come from every side, it doesn't matter.
Right.
So
the dipole is like this.
Yeah.
That means this is artificial.
yeah, and because
Perpendicular to your this.
yes, yeah. But in this case there's an option disk.
Oh, you are simulating neutron star.
Yeah, but I am not putting an angular momentum in the code. Right? Angular momentum makes it more complex. We tried something, but it was not working. So before we just started the simple case, the spherical condition होगा हर जगह से, and I have magnetic field. What would happen in that case?
And you simulate only one hemisphere.
Yeah, my hemisphere. Because the code was taking too much time to simulate all the quadrants.
Especially it was the poles.
Yeah, the poles takes too much. Poles and near the
Structure or okay, fine.
this is structure, and that too one ratio, like uniform ratio, not geometric ratio. Sir has one code with the structure, and he's not giving all that. Sir himself has a code with such structure.
I also.
He's not giving it. Okay. Any question? Yeah.
Oh, you heard about this adiabatic. You are doing adiabatic process. So I did not get you how physically you are how physically that process is adiabatic.
I mean,
How are you saying that?
I think I explained it also. That it's a simpler assumption. So,
But you are just telling that it is a simpler assumption, but then you are using it in your final code also, right?
okay, so basically, yeah, so even in sun's convection zone for simulating that, and we have a lot of results from the simulations and data, even there adiabatic conditions hold.
Okay, so basically it
Yeah.
matches with data.
Exactly. Of course, it's, you want to match the data, of course. So you start a simpler assumption, and you see where it starts to deviate or where it starts to match. P field matched for sun's convection zone also. And in MHD, in astrophysical situation, most of the time adiabatic conditions work. But if you go inside neutron star, it will not work because inside neutron star, equilibrium state is not known. That is also a new risk. That is also open problem to find equilibrium state of neutron star inside the neutron star. Because the physics there is not fluid dynamics, it's solid state, it's condensed matter physics. Okay, so you cannot really, it's a different realm of physics. Essentially, mass later. Here,
You're talking about adiabatic conditions, and then we are also talking about viscous drag, which is basically dissipating energy.
right.
Yeah, so
Right.
how can you say do both things at same time?
Yes. So essentially, I just told you before also, he is trying to ignore any kind of dissipation due to viscous drag. Saying the viscous drag dissipation will be approximately very small compared to your luminosity generated from accretion. The energy generated due to accretion will be very high compared to any viscous energy dissipation. So that's the approximation he made. But there are later models like you can add radiation terms in your equations which you have to simulate, and you can have radiation MST. Okay, so that's when you consider any kind of radiation happening. This is a simpler where you assume that there is no energy. I'm not saying there is no energy, but it's very less compared to what you're generating. So you can safely say, yeah, accretion work. It's fine. Simple.
When you're using Lorentz force, you're assuming the accreting particle is charged. Accreting particle is charged in some manner. So, and the system you are studying is neutron star and a black hole.
Neutron star. Ions in my thesis I'm studying neutron star.
Is this for that case?
Yeah.
So, if you are taking, so what are the ions that are coming from the neutron star? Like, is it accreting the neutron star itself?
Accreting on neutron star surface.
So, if it's neutron, like how is it acting? Lorentz force is acting on that neutron.
On neutron, like.
So what
is it acting on the particles, plasma particles? I didn't see like where you're confused.
The Lorentz force has to act on a charged particle.
Yeah.
So what is a charged particle like?
Plasma.
Plasma is
Like plasma. So in most of the matter is the again I don't know, but yeah, the matter in accretion is of plasma nature because the temperatures are very high. When you observe that, the spectrum, when you see the spectrum of what, they will be radiating X-ray or that spectrum. It's very high temperature. Okay, so at that high temperature, you cannot have a gas or a fluid, liquid or solid. You can only have plasma, just like this one. So using plasma. Yeah.
Probability simulation, you also predict some parameters for the star. From these simulations, you also predict any parameter for the star.
Right now, we are not doing. We are assuming. So for now, we are modeling the star as some sink where matter comes and goes, and that's it. We are not really the boundary conditions which we simulate in the code. They essentially that we say the code that any matter which is this radius, just go.
So you don't have any extra information, whatever.
Right now, for my I have, but people do. So what else can you get from these simulations? You can get the period of the star. So this is very nice concept which I recently learned. So what happens is that magnetic field, okay, and matter has an angular momentum. Okay, now you know about the flux freezing theorem. No. Okay, so in the astrophysical sense, where there is less dissipation. Okay, so when there is very low dissipation in the system, low magnetic dissipation, you can say that the plasma is frozen into the field length. So as the field line moves, plasma will move like that. Or as the plasma moves anyway, field lines also follow the plasma. Okay, so these two are both interconnected together. You can safely say they are together now. Plasma, field length and plasma. What happens is that these field lines are anchored on the star. Okay, so now these field lines act as a long arm of the star. Okay, now plasma has an angular momentum. Okay, at certain radius, this angular momentum may be higher than the star's angular momentum or lower than the star's angular momentum. So it can either spin up the star, either it can spin down the star. Can you see that? It's like a big long arm, and there is some material which is trying to move faster than the star's angular momentum. So if this is carrying this away with it, this whatever magnetic field is anchored on the star will also try to either slow it down or fast spin up. So this kind of things you can these kind of parameters, how much spin up is going, or how spin down, how much is the rotation period of the star is, and how fast it is changing, or how it is going down or is speeding up. Rather than luminosity, then you want to simulate jets and all, any jets which come out of the star. That's like luminosity of that. You can simulate all that. You can find out parameters of that. What exactly were you looking for there?
Add something new information about the system.
Yeah, like what kind of system?
Like matter distribution, what type of matter was there.
Yeah, so matter so if you say that which ions are you talking about? In the plasma,
do the X-ray. From observing the X-ray, we can say about the metal what was.
Yeah, you can expect, you can do spectroscopy and you can find out which lines are there, and usually you can also get magnetic field data also. Like what is the magnetic field value of that? You can find out the polarization of the field and the polarization type, if it is cellular polarized, whatever it is, and you can magnetic directions and everything. So I think 2022, the same group who imaged the first black hole image, they also measured the magnetic field lines of the same black hole, and a new image was generated. I think one of our alumni is also, I think Rohan Kasar, he was in that same group who imaged the magnetic field of the black hole, same M87. He's 16 MSA, 17 MSA, 17 MSA. Yeah, Rohan Kasar, yes.
16 or
17 MSA. He was RTA in the first year, so he was in the same group who imaged the magnetic field. That was the first time ever people. So the problem was, black hole, nothing can escape from it. Information can't come out of it. So magnetic field can't be anchored on the black hole surface. Okay. So the plasma around the black hole, it sustains some kind of magnetic field. Because plasma is moving in, there is some kind of magnetic field somewhere, right? That magnetic field was never observed. It was theorized that there is magnetic field in the accretion disk, but they were not observed. They finally observed in 1922 or something. It was a collaboration again with the whole Earth, like multiple satellites together imaging that. You can do lots of stuff with it. And that's what you want to do in simulation also. You want to simulate that and see can you mirror it. Anything?
Yeah, so I have a question about adiabatic condition. So in this accretion disk formation, you have some sort of sensor and stethoscope in there forming some sort of thing. In this sort of situation, it's either an exothermic or endothermic process. And with these sort of absorption energy in the disk, how do you maintain an adiabatic condition? There will be heat loss or some sort of heat.
There is a lot of it like that. There is heat loss.
So physically, how you interpret adiabatic conditions in such a
Actually, I just know that people consider demonstrate adiabatic, but then to account for those effects, they put extra terminals in the Navier blocks. Navier blocks has all kind of forces, right? So these radiation forces, to what you are saying, the brainstorm radiation, cyclotron radiation. Cyclotron is basically what? Charged particle radiating energy. That's cyclotron radiation. So these kind of radiations you want to add because these kind of radiation will be there. What's the plasma system?
assume some means sort of interaction.
Yeah. And you put those terms in Navier blocks and you simulate that along with it. And you do the same thing in the energy conservation law. In the energy conservation law, I still say energy is concerned, but it's not really. Energy is there is some energy coming, some energy dissipating, some energy absorbing. So you want to add the source and sink term also. So this source term will be some so like you were saying it's exothermic endothermic. So from where will exothermic? From which part of this exothermic? From which part of the endothermic? So you say after this radius, this term will dominate in the equation. After this radius, this term will dominate in this equation. So that's how you simulate the system. Separate and then you solve it with it. Because it just gives P and rho relation, nothing else. That's what you want to do. So that reduces the equation number which you want to solve. Simplifies. Rho and P are already related now, so you don't have to solve one rho equation, you don't have to solve that.
It's a coupled equation reducing.
Yeah. Anything else?